Lecture 9-2, the natural response of RL circuits. The objectives of today's lecture is to analyze the natural response of first-order systems and to analyze the step response of first-order systems and to demonstrate the general solution for step and natural responses. Today's lecture we will focus on RL circuits, which include a resistor and an inductor. These are first-order circuits because they can be described by a first-order differential equation. The natural response of a circuit occurs when an inductor or capacitor is connected to a DC source and is suddenly disconnected and the stored energy is released into a resistive network. The second method of analysis that we will discuss in a later lecture is called the step response, which occurs when a DC source is suddenly connected to an inductor or capacitor and it begins to store energy. The third method of analysis that we will describe in a couple of lectures is called the general method that can be used to find the step and or natural response for any RL or RC circuit.
So now let's derive the differential equation and the natural response for a first order circuit that includes a resistor and an inductor. Here we have an inductor in parallel with a resistor, and the first step in the analysis is to write the KVL equation. The KVL equation is VL plus VR equals 0. And then substituting in that the voltage across an inductor is L di dt, and using Ohm's law to voltage across the resistor is I times R, we get L di dt plus I times R is equal to 0. So now we do something that we call separation of variables. So I'm going to all of the terms that include I of t on the left side of the equal sign and all of the terms on the right side of the equal sign. So we have di dt plus R over L equals 0, and di dt equals negative I times R over L. And then I'm going to divide both sides of the equation by I and multiply by dt. So I have di over I equals negative R over L dt. And to solve this differential equation, you integrate from 0 to t on the left and right side of the equation. So the integral from 0 to t di over I equals the integral from 0 to t negative R over L dt. So that left integral is a natural log. So it's the natural log of I of t evaluated from 0 to t, and that equals negative R over L t. So now I can write the left side of the equation as the natural log of I of t divided by I of 0. And that equals negative R over L times t. Next, to get rid of the natural log, I raise both sides of the equation to the e. So e to the natural log of I of t over I of 0 is equal to e to the negative R over LT. So finally, I can write I of t as I of t is equal to I of 0 e to the negative R over LT. This is the general equation for the natural response of an RL circuit. Notice the key information we need is the initial current and something we call the time constant, which measures how long it takes to get to the final value, where tau is equal to L over R. So I can now write that equation as I of t equals I of 0 e to the negative t over tau. So the time constant for an RL circuit is tau is equal to L over R. This is significant because when the time since the DC source was removed exceeds 5 time constants, the current through the inductor is essentially less than 1% of its initial value. The time when the current through the inductor is changing or discharging before 5 time constants is referred to as the transient response or changing response, and the response that exists a long time after DC switching is the steady state response. The following figure demonstrates the effect value of having a time constant on the response. Notice that the smaller the time constant, the quicker the curve arrives at the final answer, as shown here for tau equals 0.5. It should be noted that the current in an inductor cannot change abruptly. I of 0 minus equals I of 0 plus equals I naught, although the voltage can change abruptly based upon whether the inductor is storing energy or discharging energy. Current is an exponentially decaying curve after the DC source has been removed, And recall that under DC conditions, an inductor acts like a short circuit, so we can use that in order to model the circuit right before DC switching. At that point, you can then use Ohm's law to find the voltage across that resistor that was in parallel with the inductor, or you can use V equals L di dt to find the voltage across the inductor. The left curve shows the natural response for the current through an inductor. And you see that it starts at I0, and within one time constant, it has dropped to 0.368 of I0. And in this class, we use as our standard 5 time constants to say the inductor is essentially discharged. So the other value that we typically would show on a graph is 5 tau. However, the voltage across the resistor, which is parallel with the inductor, it actually starts out at 0 volts, and then right when the inductor starts discharging, the voltage across the resistor spikes up to I0R, and then it also exponentially decays, reaching the final value by 5 tau. The power dissipated for the resistor is I0 squared e to the negative 2 R over LT. The energy delivered to the resistor is based upon the equation we have that P is equal to dW dt, or that the integral of the energy is the power. So you can find the energy delivered to the resistor as 0.5 Li I0 squared times 1 minus e to the negative 2 R over LT joules, or the energy is W equals 0.5 L I0 squared, also in joules. So the steps to find the natural response RL circuit are find the initial current I0 through the inductor, find the time constant for the circuit, which is tau is equal to L over R equivalent, or L over R Thevenin, where R Thevenin is the resistance seen by the inductor, and use the expression I of t equals I0 e to the negative R over LT, or I0 e to the negative t over tau to find I of t using I0 and tau. Any other voltage, currents, power, or energy that you need to find in the circuit, you can use the equations here, or the fact that the voltage is equal to L di dt. Now let's try example 2. For the following circuit, determine IL of t, VL of t, and IR of t for t greater than or equal to 0. Also make a sketch of each voltage and current. So the first thing you should notice is that the current source is 10 U of minus t. That U of minus t is called a step response. The step response, or the step function, is defined to be a step function that turns on at time 0. It goes from 0 to 1. So U of t is equal to 0 for t less than 0 and 1 for t greater than or equal to 0. So when you have 10 U of minus t, that means you have a function that is turned on with an amplitude of 10 amps before time 0, and then at time 0 it turns off, or it goes to 0. So 10 U of minus t is equal to 10 for t less than 0 and 0 for t greater than or equal to 0. Another way to think about this is it's like a switch. It's a 10 amp switch that turns off at time 0. The way that we analyze this circuit is we do 2 times. We draw it at t equals 0 minus, when the 10 amps is still on. That circuit is DC steady state, and we use it to find the initial current through the inductor. We draw it in at t equals 0 plus. The 10 amps is now off, and we use this circuit to find tau equal to L over R Thevenin. So under DC steady state, an inductor looks like a short circuit. So I'm going to have 10 amps, a 4 ohm resistor, and a wire. And the current through that wire is IL of 0. So IL of 0 is equal to 10 amps because current follows the path of least resistance. To find tau, the current source is now gone, and the way we turn off a current source is we make it a break or an open circuit. So I have 4 ohms and 0.5 Henry. So since tau is equal to L over R, that is 0.5 divided by 4. So tau is 0.125 seconds. So I of t is equal to I of 0 e to the negative t over tau, or 10 e to the negative 8t amps, and that's for t greater than or equal to 0. The voltage across the inductor, VL of t, is L di of t dt, or 0.5 times negative 80 e to the minus 8t, which is equal to negative 40 e to the minus 8t volts. The current through the resistor is equal to the same as voltage across the inductor, because of the resistor and the inductor in parallel, divided by 4. So the current through the resistor is negative 10 e to the minus 8t amps for t greater than or equal to 0. So when I create the sketches, we'll do the inductor first. So when I sketch the inductor, you always label your axes first, the current in amps, the time in seconds. The initial current for the inductor is 10 amps, so you have a 10, and then you show the current dying off to 0. And we mark that it essentially gets there in 5 time constants, where 5 time constants is equal to 5 times 0.125, or 0.625 seconds. The current through the resistor is at negative 10. So the initial current through the resistor was a 0, because remember the current went through the inductor. And then it drops down to negative 10, and it also starts to die off, where it gets to the final value in 5 time constants. Finally, let's show the sketch for the voltage. The voltage across the inductor. The voltage across the inductor is initially 0 volts, and then at time 0, when the switching occurs, it drops down to negative 40, and it also dies off to 0 in 5 time constants. So now let's try example 3. For the following circuit, what is the current IL of t for t greater than 0? So just like before, to analyze this problem, we draw it at t equals 0 minus and t equals 0 plus. At t equals 0 minus, the switch is closed, and we use it under DC steady state conditions to find IL of 0. At t equals 0 plus, the switch is open, and we use that circuit to find tau equal to L over R Thevenin. So first, let's draw the circuit with the switch closed and model the inductor as a short circuit. So we have 20 amps, 0.1 ohms, 2 ohms, the wire for the inductor, 10 ohms, and 40 ohms. What you should notice here is that all of these resistors are shorted out by that wire. So IL of 0 is equal to 20 amps because current follows the path of least resistance. When you open the circuit up, we now have a 2 Henry inductor in series with a 2 ohm resistor, and that is in parallel with, and that's in series with the 10 ohm resistor and the 40 ohm resistor in parallel. So the resistance that the inductor sees is R Thevenin is equal to 2 plus 10 in parallel with 40. So R Thevenin is equal to 10 ohms, and tau is equal to 2 divided by 10, or 0.2 seconds. So IL of t is equal to I of 0 e to the negative t over tau. So IL of t is equal to 20 e to the negative 5t amps for t greater than or equal to 0. So if I make the sketch, there's 3 things I care about. First one, label the axes. Horizontal axis is time in seconds. Vertical axis is the current in amps. The next thing is the initial current, 20 amps, and the final current is 0. And we estimate the time that it takes to get there as 5 tau, or 5 time constants, so it will be there in 1 second. Now let's try example 4. For the following circuit, what is the current IL of t for t greater than 0? So as usual, I'm going to draw this circuit twice. Once at t equals 0 minus, the switch is closed. DC steady state conditions. And t equals 0 plus, the switch is open. I use this first circuit to find IL of 0, and I use this second circuit to find tau equal to L over R Thevenin. So when the circuit is closed, I have 120 volts, 3 ohms, 60 ohms, 6 ohms, the current pointing up, IL of 0, and 2 ohms. Probably the easiest way to do this problem is to do a source transformation and get 120 divided by 3 is 40 amps in parallel with 30 ohms in parallel with ohms So first what we're going to do is to find the current source by the voltage source. So we get that IS is equal to 120 divided by 3 plus 30 in parallel with 6. And that's because the 2 ohm resistor is shorted out. And so we get that IS is equal to 15 amps. So since that 15 amps is divided between the 60 ohm and the 6 ohm resistor, we can use the current divider. However, one thing to note is that the current is going opposite the flow from the source. So it's going to be negative 30 in parallel with 6 divided by 6 times 15 equals negative 12.5 amps. So the initial current is negative 12.5 amps. Now I draw the circuit again with the switch open. I only need to draw the part of the circuit that's on the right hand of the switch because that's the only part that includes the inductor. The left circuit is active, but that won't affect the resistance. So here we have 2 ohms in parallel with 8 millihenry. So tau is equal to 8 millihenry divided by 2, which equals 4 milliseconds. So finally, IL of t is equal to I of 0, negative 12.5 e to the negative t over 4 milliamps. Or alternately, you can write that as IL of t is equal to negative 12.5 e to the negative 250 t amps for t greater than or equal to 0. Finally, let's look at example 5. For the following circuit, the switch moves from position A to position B at t equals 0. Determine IL of t, VL of t, and I of t for t greater than or equal to 0. So for t equal to 0 minus, we have DC steady state conditions. So we have a 30 volt source in series with a 10 ohm resistor. We can skip over the 3 ohm resistor because it's not attached. But we do have a 5 ohm resistor here. And then it goes to a 6 ohm resistor. And I have a short circuit for the inductor. And I'm looking for IL of 0. So once again, what we can do here is we see that the 5 ohm and the 6 ohm are shorted out. So IL of 0 should be the same as the current from the source. So IL of 0 is 30 divided by 10, which is 3 amps. Then we draw the circuit at t equals 0 plus. And now we're at switch B. So we have a 3 ohm resistor in parallel with a 6 ohm resistor in parallel with a 4 Henry inductor. So R Thevenin is equal to 3 in parallel with 6, which is 2 ohms, and tau is equal to L over R Thevenin, which is 2 seconds. So IL of t is equal to 3 negative t over 2 amps, t then equal to 0. VL of t is L IL of t, t. So that would be 4 times negative 3/2 e to the t2. So VL of t is equal to negative 6 e to the negative t over 2 volts, greater than or equal to 0. Since VL of t is equal to VR of t, I can use that fact to find IR of t. So IR of t is equal to VL of t over 6, which is negative 1 e to the negative t over 2 amps for t greater than or equal to 0. I will leave it to the viewer to create the sketches since it's very similar to what we did on the initial example. And this concludes today's lecture on the natural response of an RL circuit.